Welcome to CodeWhisper.
The show where we dive deep into the code and concepts behind our digital world.
Have you ever tapped on your phone, maybe typed on your computer, or even just seen a game score hit some seemingly random limit and found yourself wondering, how does this actually work? Or maybe, why did that app just crash?
Yeah, those little digital mysteries, they're everywhere, aren't they? And they often point to something, fundamental about how these machines operate.
Exactly. And today we're taking a deep dive into C programming. It's one of those foundational languages. And we'll explore the principles behind how our devices actually interpret our commands.
Right. Our mission really is to sort of pull back the curtain on all those layers of abstraction. You know, the things that let us talk to machines without, speaking binary.
We want to give you a fast track to understanding the core of how software works. And for this, we've pulled insights from some really comprehensive computer science lectures and C programming tutorials.
Okay, so where do we start? I guess the absolute bedrock, right?
Yeah, at the very bottom.
Machines, fundamentally, they only get two states. On or off, that's it.
Like a light switch.
Exactly like a light switch. We call it 1 or 0, binary.
Okay, on or off, 1 or 0. But hold on, how does something complex like, the text on the screen or the colors get boiled down to just ones and zeros? That feels like a huge leap.
It does, but it's actually a pretty elegant system. We use standards. Take text, there's something called ASCII. It basically maps numbers to letters.
Numbers to letters.
Yeah, so like number 72, then 73, then 33. If a computer reads those using the ASCII standard, it translates them into HII.
Hi-I, just from numbers. Wow, okay. So the computer isn't seeing H, it's seeing 72, which is then what? Broken down further.
Precisely. That 72 gets represented as a specific sequence of ones and zeros.
Okay.
And it's not just text. Those same numbers, 72, 73, 33, in a different context, say a graphics program, might mean amounts of red, green, and blue.
Ah, RGB. So those numbers could define a color, like a specific sheet of yellow, maybe?
Exactly. For one tiny dot on your screen, 1 pixel.
Right, 1 pixel. And if you have millions of those pixels, each with its own color defined by numbers,
then you get a full image.
And if you show those images really, really fast,
you get video, animation. It all builds up layer by layer from those simple ones and zeros.
Which brings us right back to abstraction, because thankfully we don't have to sit there writing ones and zeros all day.
No kidding. That would be painful.
We use higher level languages. We talked about Scratch before, right? With the visual block.
Drag and drop. Very intuitive.
Well, today we're getting into C. It's text-based, looks maybe a bit more cryptic at first glance.
It can seem that way, but it gives you incredible power. And these languages, these abstractions, they let us think about problems in a more human way.
We can focus on the what without getting totally lost in the how of every single transistor flipping.
Right. But even with these abstractions, you still need to be incredibly precise. A computer, at its heart, just does 3 things. Yeah. Takes input, does something, and gives output.
And that's something in the middle. That's the algorithm, the recipe.
And how good that recipe is, how efficient, really matters. Think about finding a name in an old phone book.
Okay, yeah. Big, thick book.
You could go page by page, right? Start at A, flip, flip, flip.
That would take forever for Smith. That's linear search.
Yep, linear, very slow. What do you actually do?
Well, I'd probably flip it open somewhere near the middle, maybe around M, then see if Smith is before or after, and jump again.
Exactly. That's divide and conquer. Way, way faster. Open, middle, check, narrow it down, repeat. That's a much more efficient algorithm.
But that highlights something else, doesn't it? When I say open the bread, or call Mike for making a sandwich,
yeah,
I assume a lot. You know what bread is, how to open a bag, how to use a phone.
Right. Humans fill in the gaps constantly. But a computer, or a robot, you have to tell it everything.
Like pick up phone receiver, move receiver to ear, press button 7, press button 2. Extremely granular.
And ambiguously granular.
Yeah.
Because if you miss a step, or you're not precise enough,
that's when things go wrong. The program crashes.
That's often it. You get the spinning beach ball, or the hourglass. The computer's basically stuck because your instructions weren't clear enough. It doesn't know what spread the jelly really means in terms of motor movements and sensor inputs.
Okay, so we've got binary, abstraction, algorithms, the need for precision. Now let's actually look at C code. How do these ideas turn into something you type?
Right. Moving from, say, Scratch's blocks to C's text, it looks different, sure. More symbols, maybe?
The classic first program is always hello world, right? It's like print hello world or something.
That's the core of it, yeah.
Yeah.
Print is the function to print something to the screen.
But there's usually other stuff around it, isn't there? Like hashtag include something and int main void.
Ah, yes. The overhead, you could call it, hashtag include stdio.ouch, is basically telling the compiler, hey, I'm going to use some standard input-output functions like print. You can find the info about them in the stdio.file.
So it's like importing a toolkit.
Kind of, yeah. It's a header file and int main void. That's just the official starting point. Every C program starts running inside that main function. It's like when green flag clicked, block and scratch.
Okay. And those little things people always complain about, like forgetting a semicolon or messing up parentheses.
Yeah, the syntax. It's like grammar. C has its own specific rules. They can be annoying at first, definitely.
But they aren't the big ideas.
Not really. They're just the rules of this language. The underlying concepts, functions, variables, loops, those are the important parts that transfer across many languages. You get used to the semicolons.
So print stuff, you said it prints stuff. What about that N? And I've seen things like percents or percenty inside the quotes.
Good questions. The N is a special character sequence that means new line. So it prints hello world and then moves the cursor down.
Ah, so the next thing printed isn't right next to it.
Exactly. And the percent antecedent, those are format codes. The F in print actually stands for formatted. Percents means insert a string here, and percent means insert a decimal integer here.
So you can stick variables into the text you're printing.
Precisely. You'd have print, my name is percent, and I am percent years old. Name variable, age variable, something like that.
Okay, that's output. How do we get input from the user? Like asking for their name.
C has ways, though sometimes they feel a bit clunky compared to simpler languages. You might see scanf, but it can be tricky. Often helper libraries like CS50 provide easier functions like getString or getInt.
So the program pauses and waits for me to type something.
Yep. You type your name, hit enter, and the getString function grabs that text and gives it back to your program, usually to store in a variable.
And just like we can make our own blocks in Scratch, can we make our own functions in C? Like a function to cough?
Absolutely. That's fundamental. You can define your own reusable pieces of code. You could define void cough, void, to just print cough.
Void means it doesn't give anything back.
Right. But you could also make it take an input, like void cough, and n, where n is the number of times a cough. Inside, you'd have a loop that prints cough and times.
So you could call cough.
Exactly. And functions can return values, too. Maybe a function calculates something and returns the answer, like handing you back a result on a piece of paper.
Okay, functions are like verbs.
Right.
What about the nouns, the data itself? You mentioned variables.
Right. Variables are just named containers for storing data, like X and Y in algebra. But in C, you have to be more specific.
Specific how?
You have to declare the type of data the variable will hold before you use it.
Ah, okay, so you can't just say X equal 5.
Nope. You have to say int X equals 5 if X is going to hold whole numbers, integers. Or char C equals A for a single character. Float price equals 9.999 for decimals. String name, Alice, for text.
So init counter equals 0 means create an integer variable called counter and put 0 in it.
Perfect. And that single equals sign is crucial. It means assignment, not equality like in math.
Assignment, you mean copying the value?
Yes. Counter plus 1 doesn't ask is counter equal to counter plus 1. It means calculate counter plus 1, then store that new value back into the counter variable.
Replacing the old value.
Exactly. Which is why counter plus 1 makes sense in programming. And there are shorthands like counter plus 1, or even just counter plus plus, which both mean add 1 to counter.
Okay. For assignment, how do you check if things are equal then? Like in a decision?
For comparison, you use the double equal sign.
Got it. So that's used in conditional statements, like if statements.
Exactly. You'd write if X,
right.
Y, do something. That checks if the value in X is the same as the value in Y.
And you can have else if and else too for more complex choices.
Yep. If condition 1, S, if that's into S creates branching paths in your code.
And can you combine conditions, like if X is greater than 5 and Y is less than 10?
Sure can.
Yeah.
You use logical operators N and A for A and D for OR. So if my 5 and a Y 10, there's also for not.
Okay. That gives programs decision-making power. What about doing things repeatedly? Loops.
Loops are essential for automation. You mentioned the cough3 function using a loop. One common type is the for loop.
How does that work?
It's really neat for when you know how many times you want to repeat something. The syntax looks like for int I is 0, I 10, I++.
Whoa, okay, break that down. Int I equals 0.
That initializes a counter variable I to 0.
I 10.
That's the condition. The loop keeps running as long as I is less than 10.
And I++ I.
That happens after each run through the loop. It increments I by 1. So it runs for I equals 0, 1, 2, all the way up to 9. 10 times total.
Clever. Very compact. Are there other kinds of loops?
Yeah, there's the while loop.
Mm-hmm.
While it just keeps running as long as the condition is true. You have to make sure something inside the loop eventually makes the condition false or...
Infinite loop?
Yep. Sometimes useful, often a bug. There's also do while, which is similar, but guarantees the code inside runs at least once before checking the condition.
Okay. Variables hold single values. What if you need a list of values, like test scores for a class?
For that, you use arrays. An array is a container that holds multiple values, but they all have to be of the same data type.
So an array of integers or an array of characters.
Exactly. You could declare int scores 30 to hold 30 integer scores.
And how do you get to the individual scores, like the first one or the 10th one?
Using an index number inside square brackets.
Oh.
Crucially, indexing starts at 0.
0, not 1.
0. So score 0 is the first score, scores 1 is the second, and scores 29 would be the 30th score in our array of 30. It trips people up at first, but it's fundamental.
Okay, 0-based indexing. Got it. And you mentioned strings earlier, like string name. Is that related to arrays?
In C, traditionally strings are arrays of characters. So char name 20 would create space for a name up to 19 characters long, plus a special null character at the end to mark where the string finishes. Newer helper libraries might give you a simpler string type, but underneath, it's often still an array of chars.
Arrays hold multiple things of the same type. What if you need to bundle different types together, like information about a student, name, string, age, int, GPA, float?
Ah, excellent question. For that, C gives you structs, which stands for structures.
Structures.
Yeah. A struct lets you define your own custom data type that groups together different variables. You could define a struct student that contains a string for the name, an int for the age, a float for the GPA, maybe another string for the major.
So it's like creating a template for student.
Exactly. It's a blueprint. Then you can create variables of that type. So you could have struct student Alice and struct student Bob, and each one would have its own name, age, GPA fields inside it. It lets you model real-world things very effectively.
That sounds really powerful for organizing complex data.
It absolutely is. It's key to building larger, more organized programs.
Okay, so we've written all this C code, our source code, using functions, variables, loops, maybe some structs. But you said the computer, the CPU, only understands machine code, the ones and zeros. How does that translation happen?
That's the job of the compiler, a program like Clang or GCC.
The compiler is?
Yeah.
Another program?
Yep. A very complex program written by very clever people. Its whole purpose is to take your human-readable C source code file, like hello.c, as input, analyze it, make sure the grammar syntax is right, and then translate it into the equivalent machine code instructions that your specific CPU architecture understands.
So it's a translator, source code in, machine code out.
Precisely. It bridges that gap.
And how do you actually use the compiler? It's not like clicking a green flag in Scratch.
Usually no. They typically work in a terminal window, a command line interface.
The black box with text?
That's the one. You type a command like clang hello.cho hello.
Okay, clang is the compiler. Hello.c is my source file. What's oh hello?
O means output file. So oh hello tells the compiler, please name the resulting executable machine code file hello.
Ah, so it creates a new file named hello that I can run.
Exactly. Sometimes, especially in learning environments, you might just use a simpler command like make hello. Make is another tool that often automates that clang command for you, figuring out the right options based on the file name. It's just a convenience.
Okay, so I compile it, I get this hello file, how do I run it?
Back in the terminal, you type .hello.
/. Yep. That tells the terminal, look in the current directory for the program named hello and run it.
And then I should see hello world printed.
If all went well, yes. But here's the crucial part. If you go back and change your hello.c source code, you have to recompile it before you run it again.
Oh, right. Because running .hello runs the old machine code version.
Exactly. The computer only runs the compiled code. You change the source, you must recompile to create a new machine code file reflecting those changes. It catches everyone out at first.
Okay, that makes sense. Recompile after every change. You mentioned header files earlier, like stelio.h. What's the role again? They contain declarations or prototypes for functions defined elsewhere. ASCII.h tells the compiler what print looks like, what inputs it takes, what it returns, if anything, but not how print actually works internally.
So it's just enough info for the compiler to check that I'm using print correctly in my code.
Precisely. The actual machine code for print is usually in a precompiled library that gets linked in later in the process. Mm-hmm. It's another form of abstraction you can use print without needing to see its complicated internal code.
Okay. So we can compile, run. Can C programs also work with like actual files in the computer, reading data from a file or writing results to one?
Oh yeah, absolutely. C has functions for file input, output, or I/O. You'd use functions like fopen to open a file, specifying if you want to read R, write W, which overwrites, or appends.
And then you can read lines using something like faggots, or write formatted text using a frint.
Exactly. fprint works just like print, but it writes to a file instead of the screen.
Yeah.
And you always need to remember fclose to properly close the file when you're done. You typically work with a file e variable, which is a pointer storing the memory address associated with the open file.
Pointers. That sounds like it could lead to complexity.
It can.
Yeah.
Which actually brings us nicely to some of the, let's say, unseen challenges and weird consequences that pop up because of how computers fundamentally work.
Like what?
Well, remember how computers have finite memory? Finite RAM.
Yeah.
That means they can only represent numbers up to a certain size. An integer variable, for instance, might only have 32 bits of space.
Okay. So what happens if you try to store a number bigger than that?
It overflows.
Mm-hmm.
Imagine an old mechanical counter, like for mileage in a car. If it only goes up to 999, what happens when you add one more?
It rolls back over to 1000.
Yeah. Exactly. That's integer overflow. In a 3-bit binary system, the biggest number is 7, which is a 111. If you add 1 to it, you get 1,000. But if you only have 3 bits, that leading 1 gets lost, and you're left with 000. It wraps around.
Huh. Does that actually happen in real software?
Oh, absolutely. Remember those old arcade games where the score maxed out at a weird number, like 4 billion something?
Yeah.
That's often because the score was stored in a 32-bit integer, and that's roughly the maximum value it can hold. Adding one more point makes it wrap around, often to 0 or negative number.
That's kind of funny in a game, but I bet it can cause serious problems elsewhere.
You bet. There was a major issue with the Boeing 787. A counter in the generator control unit tracked time in hundredths of a second using an integer. If the plane was powered on continuously for 248 days, the counter would overflow. And the result, the generator would just shut down, potentially mid-flight. They had to issue an order to periodically power cycle the planes.
Wow. Just from a number getting too big. And the Y2K bug was similar, wasn't it? About limited space for data?
A very similar principle. Storing years is only 2 digits, 99, for 1999. When the year rolled over to 2000, sortings could be interpreted by older systems as 1900, potentially causing chaos in calculations for loans, schedules, everything. Billions were spent fixing it. It's all about the limits of representation.
And it's not just whole numbers, right? You mentioned decimals earlier.
Right, floating point numbers. Representing numbers with decimal points is also tricky with finite memory. How do you store something like 13 perfectly, which is 0.3333, forever?
You can't, really. You have to round it at some point.
Exactly. And because computers use binary, even seemingly simple decimals like 0.1 can't be represented perfectly. So you might find that in C, calculating 0.1 plus 0.2 doesn't give you exactly 0.3.
Really? What does it give you?
It might give you something like 0.3000000000000000004. A tiny, tiny error.
Does that tiny error actually matter?
It can accumulate. Imagine doing millions of financial calculations. Those tiny fractions of pennies can add up. Or calculating a rocket trajectory. A tiny error early on can lead to being miles off course later. Using double precision variables helps, giving you more bits, usually 64, but it doesn't eliminate the fundamental issue.
So overflow is when numbers get too big. Is there an underflow?
Yes. That's when you subtract from a very small number and it wraps around the other way, often becoming a very large positive number.
How could that happen?
There's a classic, maybe apocryphal story about the game Civilization. Gandhi's aggression level was apparently stored in a single byte, 8 bits, so 0 to 255. He started at 1, very peaceful.
Okay.
Then, if you adopted democracy, the game apparently subtracted 2 from your leader's aggression, subtracting 2 from 1.
Would underflow.
Like,
the wrap around
to 255. Maximum possible aggression level. Suddenly, peaceful Gandhi becomes nuclear weapon-wielding maniac Gandhi.
No way. That's hilarious, all from a simple subtraction going wrong.
It shows how these low-level details can have really unexpected, sometimes comical, consequences. And speaking of low-level, we should briefly touch on pointers. You mentioned file E.
Yeah, what are pointers, really?
Think of your computer's memory, its RAM, as a huge sequence of numbered mailboxes. Every piece of data, every variable lives in one or more of these mailboxes, and each mailbox has a unique address, like a house number.
Okay, like a memory address.
Exactly. A pointer is simply a special type of variable whose value is one of those memory addresses. It points to where some other piece of data is stored.
Why would you need that? Why not just use the data directly?
Pointers are incredibly powerful in C. They let you do things like pass large amounts of data to functions very efficiently, just pass the address, not copy the whole thing, manage memory dynamically, and build complex linked data structures. You use the ampersand and get the address of a variable, like add my variable, and the asterisk to dereference a pointer, meaning to get the value at the address the pointer holds, like my pointer.
Sounds potentially confusing.
Yeah.
And maybe dangerous.
They're definitely one of the trickiest parts of C to master, and misuse of pointers is a common source of bugs and crashes. But they're fundamental to how C interacts with memory directly. One last thing on code itself. Comments.
Oh yeah, the notes inside the code.
Exactly. Lines, starting with, or blocks enclosed in, the compiler completely ignores them. They're purely for humans.
To explain what the code is doing.
Yep. Crucial for anyone else reading your code, or even for yourself when you come back to it 6 months later and wonder, what was I thinking here? Good comments are essential.
Wow. Okay, so we've gone from the absolute basics, ones and zeros.
Right up through abstractions, C syntax, functions, variables, loops, arrays, structs.
Then how the compiler translates it, how we run it.
And even dived into these weird consequences of finite memory overflow, underflow, floating point issues, and pointers.
It really feels like understanding how it works, even at this level, demystifies so much about using computers. It's not just magic anymore.
Exactly. Knowing about the layers, the compilation step, the hardware limits, it gives you a much deeper appreciation for what's happening under the hood every time you interact with a device. It's an intricate dance.
So here's a final thought for you. Next time your favorite app glitches, or a calculation seems slightly off, or maybe something just behaves weirdly,
Instead of just getting frustrated,
maybe pause and wonder, could this be a subtle integer overflow? Is it a tiny floating point error accumulating? Or maybe just a logic bug, a place where the human programmer wasn't quite precise enough in their instructions?
hopefully this deep dive gives you a new lens to look through, a new curiosity about the invisible architecture shaping our digital experiences.